Hello everyone, so in this particular video we will be implementing the whole of convolutional neural network in PyTorch. So without any further ado, let's get started. So the first thing that we need to do is import certain libraries. So first we are going to have NumPy, so import NumPy as NP. After that we will also need train test split, so we will say from sklearn.model selection import train test split. You can also use random split in PyTorch. After that we will also need pyplot, so import matplotlib.pyplot as plt. After that we need torch, so we'll say import torch. We'll also import torch. We will also need torch.nn as nn, and from torch vision we need datasets. So we'll need datasets and we'll also need transforms. Okay, so let's run this. After that, for the dataset, we are using a very famous dataset, mnist dataset. So we will be doing a multi-class classification. We will be having 60,000 images of different digits, all 0 to 9, and then we will be also having the associated labels. So we will say mnist dataset equal to datasets dot mnist, and then we'll have to pass in some parameters. So we'll say root data. After that we will say train equal to true, and last we will also say download equal to true. So we will run this and hopefully, yeah, you can see it is downloading. After that we will need to get the data and target. So we will say data comma target equal to mnist dataset dot we will say data, and here we will say mnist dataset dot targets. So we'll run this particular cell and it has run. So we can see data dot shape. We should get 60,000 cross 28 cross 28. So 60,000 images we have got, and then each image is of 28 cross 28 cross 28 height and width. Now I'm not going to show you the images because you already, I think all of us are familiar with the mnist dataset, so we can not waste our time there and straight away get to the point. So now what I need to do is I need to break this dataset into train and test. So we will say train and validation. We will say train x validation of x and train underscore y and val underscore y. Now we will say train test split because we have already gotten that, and here we are gonna pass, let's say, train, or rather data, because this is our data, and then we have targets. After that we'll pass the random state, I cannot type today, random state. After that we need to pass the test size, so I'm keeping it really small, only 10%. I usually keep it 10% or 12%. Okay, this has to be target. Okay, fine. After that what we can pass is stratify. Now this is new one, stratify. What this will do is we will say stratify on target. Now why we need stratify is basically there all the images are not like equally divided. So if you can see there are 60,000 images, if we divide it by 10, it doesn't mean that 0 has 6,000 and 1 has 6,000, 2 has 6,000. No, there are some even though mnist is a very balanced kind of a data set, however there is still some discrepancy. My point is that if you want to divide it between train and test, it shouldn't be that some of the images are more in the train, and like for example train has 98% of zeros and test has only 2% of zeros. No, whatever is the data set, even if it is unbalanced, even though mnist is balanced, even if our initial data set is unbalanced, however after splitting the distribution of the label should be same. That is what I'm saying. So we'll run this particular cell. You can also go and see the documentation, and specific there you can see stratify as a parameter and read on it. Okay, after having done this, what we need to do is we need to have a custom data class. So we will say cust dat, and then we are going to say torch.utils.data.dataset. Now what we need to do is we need to give an init function. So we will say init self. Okay, we will just leave it till right now, or what we can do is we can say we can give df and or rather let me just give images and then target. Okay, now what we are going to do is we are going to have, let's say, self dot images is equals to images. This is basically your train or test, whatever that is, and we will have test self dot target is equals to, or let me just say targ, otherwise okay, target also is fine, is target. Okay, now what we are going to do is we are going to define our functions. We will say self and then we will say return, and we will say len of self dot images. So whatever is the length of the images will be returned over here. Okay, this is going to be all our images. So the next one is get item. We have already seen all of this, right? We have already seen the videos before of how to use it. So idx is going to be our index, so we need to take the image. So we'll say img image is self dot images from idx. Okay, so let's try to return it and see what we actually get, so that we can be sure that we are doing the right thing. Okay, so after this what we do is cust dat, and then we are going to have, let's say, images. Let's say we are passing it train x, and then let's say also test, no, train underscore y. Okay, and then here we will have get item of 0. Let's see what we get. So it's taking some. Okay, so what we have got is basically you have got the image, you have got a tensor. Now two things that I can see. The first thing that I can see is the values are from 0 to 250, or okay, it will be maximum till 255 because the d type is uint. Now I have told you, I think before, or if not I'm telling you right now, you cannot use any other data type other than float if you want to do backpropagation. Now that is number one. Another thing that I want to do is I want to divide it by 255 because I know 255 is the largest and 0 is the smallest. So when I divide by the largest number, the entire image is going to be normalized. Fine. So this is what I have done over here. After that, what I'm going to do is say, let's say I'm going to take tar, which is going to be the target. It will be self dot target of index idx. Okay, now I know this particular is tensor, this one here, because that's how we got it. Why not let's return target itself and see whether this is in tensor or not. I believe it will be in tensor. Yes, it is in tensor, so we don't have to convert it. Okay, what next? Okay, let's do a transform. transform equal to null. So what is transform? Basically, let me first write the transform over here. So since mnist is such a beautiful data set, you don't really have to do a lot of transforms with it because it is meant for practical, for educational purposes, and so you don't have to do a lot of things. It is already very small. It's 28 cross 28 and it's not even having a lot of it's very simple and balanced, so you don't have to do a lot of tricks in the transform. However, let me just write one particular transform because that is important. We'll say transform equal transforms dot compose, and then we are going to say brackets transforms. So after this, what you're going to do is we are saying transforms dot normalize. I'll tell you what this is. So what this does is basically it will take our image and all the values will be from will be standardized, means it will have 0 mean or whatever we are giving, this mean and this variance. Okay, so it will be standardized along these things. Okay, 1307 comma, and here you are gonna have 0.3081. Now how I got these values, you can calculate it yourself, but I got it from the internet. Okay, because this is so common data set, such a common data set that you will find it everywhere. So many tutorials on this. So we will say transform, and here we are going to say if, okay, here let me write self dot transform equal to transform, and here we are going to say if self dot transform is not none. So if we are passing some transform, then image equals to self dot transform of image itself. Fine. So we are going to, okay, there is some error. I almost forgot. To use this transform, you have to have a, okay, I'm going to explain it here. So to use this transform, you should have in the format C, H, W. What this means is you are going to have C channels and then height and width. Here what we are having is here we are just having height and width. Okay, so we need to introduce C. Now what is C? Number of channels. You know mnist dataset is only black and white, so the number of channels will be 1. So right now it is okay, it's already commented. Right now it is 28, 28. What we need? We need 1, 28, 28. Now if you remember how to do it, you are just basically going to say none and triple dots over here. If you remember, I had made a video and even used it in, I think, in logistic regression or something, that if you use none over here and then comma and triple dots, it adds unidimension at the start. So now if we are going to do this and then going to hit this one, I think it should run. Yeah, you can see. Now if you remember earlier, there were values from 0 to 1. So here you can see all the values are now between 0 and 1. Now most of them are 0 minus 0.4242 because of the zeros, and here you can see there are some other values also. Okay, but it is in the range of it is very close to 0. That's the point. Okay, so what we are going to do is now let's remove the output. Now what we are going to do is we are going to say we are going to need our data loader. So we are going to say train dl is equals to torch.utils.data loader. Okay, after that we are going to instantiate the class. We'll say cust.dat, and then let's do it for the train first. Train x train underscore y. Let's pass the transform. After that we need the batch size, since we are dealing with batch size, since we are dealing with images, even though we can have a lot more than 16 because the images are very small, but let's just keep it till there. Okay, so after that let's have shuffle also, even though I think train test does give shuffle. Let's say number of workers equal to 2, and pin memory we don't require it right now because we are not using GPU. Okay, let's do the same thing for validation. Let's say val dl, and here we are going to say val of x. Here we are going to say val of y. Fine, let's run. So it has run, and now what we need to do is we need to define basically the class. Now this is going to take some time, so bear with me and listen very closely. So first we will do a class, whatever your name that you want. I usually use net or model, and then nn.module, and in the next line what you need is you need to have an init function. Okay, and then we are passing self, and that's it. Next line we'll do super. We'll say net comma self, and then we will do init. Okay, now this is very important, and this is actually the main thing that you need to understand in this particular video. Okay, initially what will be our dimension? Since we see that we are using 16, it will be 16. I'll explain what is 16. And then our each image was converted from 28 cross 28 to 1 comma 28 comma 28. So this is the initial this is how every batch of data will look like. The batch of data will be 16 images, and each image has one channel, and height is 28 and width is 28. So this is how all the data will be given to the model. Now if you remember from the convolution video that the previous video, then if you remember there, if we don't use padding, and like you can plug the formula, you remember the formula, right? The formula was something like this. If you do not remember, or if you haven't watched the last video, it was totally optional, because if you are already familiar with that, why will you watch that video? So let's say output equal to, the formula was n minus k plus 2 times p this was divided by s, and after this all of it was added to 1. Okay, so n was the size of input image, which is 28. Again we are having a square image, so 28 minus k we will see, and p is padding, s is stride. Fine. So what I'm going to do, we are going to use what we saw in the last time. If you remember, if we use let's say I'll show it here only, say conv1 equal to nn dot conv2t, and just hold on for a second. Okay, first what we need to do is pass in the in channels. You can also see in the pop-up over here it says in channels. Okay, so in channel is, what is the channel that we are entering? It's 1, right? So our image has 1 channel. Now the second one is out channel. Out channel, this is totally upon us, so I will assume it to be 18. I will keep 18, you can keep 16, you can keep whatever you want. Okay, depends on your requirement. Now third is kernel size. Kernel size I'm taking at 3. Okay, and what I'm also doing is let's say stride is always stride is already 1, so we will not. Okay, let me just write stride equal to 1, even though it is taken by default. And then what I'm going to do, I'm going to add padding of 1. Now if you remember, in the last video I had shown, or you can also see over here and understand for yourself, it's not important, it's important, but you don't have to go back to the video. What you need to do is you need to use this formula. N is 28. Okay, I'm going to use this formula and going to show that we'll again get back 28, and hence there will be no reduction in size. What is the kernel? Kernel is 3, because kernel size is 3. Okay, and 2 into padding, so padding is 1, so 2 into 1 is 2, so plus 2. Okay, then we need a bracket over here, and divided by s, s is 1, and then we also need one more bracket, and then add a 1. Now if you look, 28 minus 3 is 25, 25 plus 2 is 27, 27 divided by 1 is 27, and 27 plus 1 is 28. So if you do that, you get back 28. So our input image was 28, and our output is also 28, which means this particular operation doesn't change the size. So size after this operation is also, if I'm going to use, yeah, size after this operation also is also going to be 16 comma. Now after this operation you have 8, the channels has increased, so the channels will increase. Okay, and the size is going to remain the same, so 28 cross 28 only. Now why did the channel increase? This is something that the number of feature maps. So in the last video I only showed one feature map. You can have multiple feature maps and the concept is going to remain the same. Okay, so this is what we are going to get after this particular operation. Okay, and I'm going to write the shapes after every operation. Okay, now if you remember maxpool, we'll just say maxpool, and let's call it 1, and then nn dot capital max pool capital max pool 2d. What we need to find, what we need to pass, we only need to pass one particular compulsory parameter, that is a kernel size. I'll just keep it to 2. Okay, so what will happen is, now if you remember max pooling, it will take a 2 cross 2, since we are given 2, it will take 2 cross 2 what to say, your box, and then try to find the maximum value in that, if you remember from the last video. So what this is going to do is, this will change our shape. It will say 16 comma 8, because number of images is going to change, number of channels has not changed, however the height and width will change, because now we are taking 2 cross 2. So if you remember, 28 will be divided by 2 divided by n. Okay, after this we will be using a relu. Let's just call it relu 1, even though you don't have to define relu all the time, but only for understanding I'm going to define it. And even after this, relu does not change the size of anything, so we will have 16 comma 8 comma 14 comma 14. And now what I'm going to do, I'm going to do one more convolution operation. Okay, so I'm going to say conv2. Now in channels here was 8, because here we are having 8, so our in channels here is 8. Let me convert this to 16. We are increasing the number of channels, and we'll keep this same. This does not change this formula, because number of channels are not there. Only in place of 28, now we'll be having 14. So again, if you do 14 minus 3 is 11, 11 plus 2 is 13, 13 divided by 1 is 13, and 13 plus 1 is 14. So whenever you have stride equal to 1, padding equal to 1, the size of the image doesn't change. I mostly almost all of the time just use stride equal to 1, padding equal to 1 if I don't have to change the size of the image in convolution. Only some of the specific cases, like for example, if I'm remembering correctly, I think in unit it is used, and I think in max faster RCNN also it is used. Okay, so those are papers, we'll discuss it sometime else. So after this operation, what will happen? Everything is going to remain the same. So it's going to be 16, 8, 14, 14 only. Sorry, 16, 16, not 16, 8, because the number of channels has changed. Okay, so remember, the number of channels has changed, and hence from 8 it has become 16. Now what we are going to do, we are going to do a max pool operation. Now we will call it max pool 2. Okay, again max pool also, here also you don't have any learnable parameters, so you don't really have to say max pool 2. You could use max pool 1 again, but you know, it comes through experience, so just use it. Now obviously this will change our shape of the image, so this will make it 16, 16, 7, 7. Why? Because max pool of 2, so it will divide the image into divide the image into two kind of boxes, if you remember from the last video, and you will have 16, 16, 7, 7. Now what you need is to do flattening. However, we won't be doing flattening over here because we will be doing it in the forward method. So what we can do, we can directly write the linear layer. So we can say FC. If you remember from the last video, you can use remember the pipeline over there. It showed that after the max pooling and there was flattening, which we will do in the forward function, and after flattening there was linear. So we will say nn.linear. What is the input dimension? So batch size we don't need. We will say 16, 7, 7. Why? 16 your number of feature maps, and each feature map is of 7 cross 7. So you will have each feature map is 7 cross 7. For that we have 7 into 7. And how many such feature maps? 16. So we will have 16 into 7 cross 7. How many digits we want at the end? Obviously 10 digits, 0 to 9. So we will say 10 output units. Fine. So last we will also need okay, we will not need anything else. So this is all for definition. Next we will have to write our forward function. So after this, what we are going to have, I'm just commenting it right now. After this you are going to have is after, let's write it over here, flatten. After flatten, this I'm doing it only so that you are it is easy to understand. We will have 16, 16 into 7 into 7. Fine. And after this, over here also it will be over here it will be 16, 10. Why? Because after linear, passing through the linear layer, 16 images, the batch size is 16, so it will remain. However, we are having 10 over here. Okay, so this is the entire way, what to say, your dimensions of the input data. Now we are going to say forward. We are implementing the forward function. Okay, so we'll say out of 0. Now out of 0, what is the first? We are going to pass it through the conv1 layer. Okay, so conv1 layer. Here I have forgotten to write the relu, but it doesn't matter because relu2 nn dot relu. It doesn't change the size, so it will continue to be 16, 16, 7, 7. Okay, so conv1 of x. Now this will be passed to self dot max pool of 1. And what will be the input of this? It will be out of 0. So first we are going, whatever the input that we have, whatever data we have, it was first passed through the convolution layer and the output was out of 0. Now whatever we got, we are passing it through the max pool of 1. So obviously now you know the drill. So we will say out of 2, and whatever the output was there, we will pass it through the relu function, relu of 1. Okay, and then we will say out of 1. Now out of 2 is here, so now after the relu first we have con2, so we will say con2, and then we are going to pass out of 2, and we are going to call it out of 3. Okay, after out of 3 there was, after this convolution 2, there was max pool, so we will say out of 4. We will say self dot max pool of 2. We are going to say that, and then we are going to pass out of 3, and out of 5 is equals to self dot relu 2. Relu 2. We are going to say out of 4. So we came till here. Now what we need to do is we need to flatten it. So the way PyTorch flattens it is, let's say out of 6 torch dot flatten. What we are going to flatten? We are going to flatten out of 5 and 1. Now what is 1? It just says that skip the 0th dimension, which is 16. This is the batch size, and after every dimension, here you can see, skip this, and we started flattening from 16 into 7 into 7, right? So we started flattening here. So 1 says that you skip the 0th position, and from the first position you flatten everything. Okay, so we have come till here. Now after flattening, what we did, we passed it through the linear layer. So we say out of 7 is equals to self dot fc, and then we are going to say out of 6. Okay, after that what we are going to do is I think we are done. Yeah, now we'll just return out of 7. Now we are going to hit the shift plus enter. Now we are going to say model equal to net open close bracket and hit. So what we are having here is one convolution operation, then one max pooling, and then relu. After that we are again having one convolution, one max pooling, and then we are also going to have a relu. Okay, after that we flattened it in linear. You can have more max pooling and convolution layer if you want. It totally depends on your architecture or whatever you want to do. Okay, now we need to define the loss function. We'll say loss function equal to nn dot. Now since we are doing multi-class classification, we are saying cross entropy loss. Okay, and then optimizer equal to torch dot optim dot stochastic gradient descent, and then we are going to optimize the model parameters. So model dot parameters, and learning rate is equals to 0.01. Now we are going to run this particular cell, and now what we need to do is we need to define the training loop. Okay, so we'll say number of epochs and let that equal to be 10. You can do it 100, even 10 takes some time. So we'll say number of for epoch in range num of epochs, and then what we are going to do is we are going to say epoch loss. So we'll say train epoch loss equal to 0 and val epoch loss equal to 0, because we are going to have both training and validation. So we'll say train underscore loss equal to open close bracket and val underscore loss equal to open close bracket. Now what we are going to do, we are going to iterate through all the examples in the data loader. So we'll say for data comma target in train underscore dl. So we are going to have this, and we'll say model, and then we'll pass in the data. So data will be of the format, if you remember, 16 comma 1 comma 28 cross 28, and then we will say we got output here. Now we are going to find the loss, and this is common in all of the PyTorch programs. This is how you do it. So you say loss equal to loss underscore fn. We are going to pass in output, and then we are going to pass in the target. Fine. After that we will say train epoch loss plus equal to loss dot detach, and then we are going to say numpy. Okay, after that we need the 3 lines that we write in all the programs. We'll say optimizer dot 0 grad, we need loss dot backward, and we are going to say optimizer dot step. After having done this, we also need to check for the validation, right? So for that we will say with torch dot no grad, which basically means that we are not going to have gradients, which in turn means that there will not be any back propagation and hence training. So for every data comma target in val underscore dl, what we are going to do is we are going to repeat the same things. We are going to say output equal to model of data, then in the next line we will have loss equal to loss function, and we are going to pass output and target. After that we will say val epoch loss plus equal to loss plus loss dot detach dot numpy. After having done that, we don't need to do anything inside the loop, so we'll get outside of the loop, and then we will say train underscore loss dot append, and here we are going to write train epoch loss, and after that what we are going to write is we are going to say val underscore loss dot append, and then we are going to say val epoch loss and let's run it and see if there are some error or not. Okay, so the training is over here and this appears to be correct. However, if there is an error, I'll let you know, and this particularly may take some time. Okay, now in general I have just written 10 epochs. You should write 100 epochs and then see how your training loss is there. For that I'm writing the code over here how to plot the loss. So we'll say plt.plot train loss, yeah, it's enough. So train loss, and here we are going to plot another one. Is a plt.plot, we are going to say val underscore loss. So I'm going to stop it right now, and when it trains I'll come back and show you the results. So the output has come out, and if you plot the train loss you get a decreasing graph. Looking at the graph, as you can see, it is the steepness has decreased. So I think at this point you can reduce the learning rate and see, but I think this is enough for mnist, and even the val loss is kind of decreasing. There is a slight bump here, however it is still, the trend is decreasing. So I have written some additional code here, as you can see. So it's basically, this one is taking an integer from 0 to val shape, val of x, because val of x was not used to train, so the model hasn't seen these images. Even though we used it for validation accuracy, but still, just to take one example, so whatever is the shape of val x, how many ever examples are there, just take one number from there and then find the image, and let's say ig is the image and val x was the images, and of num, which is this random integer, and then you take the image as ig. You take the same image as img also, but here you increase the dimension, you add a channel which is 1, and then convert it to float and divide by 255, and then target is val of y of num. Now for prediction you need to get the model, and in the model you need to pass the transformed version of image img. So once you do that and find the argmax, because if you can if you see that the model is supposed to give you 10 values, right, depending basically saying which probability is the, or what are the probabilities of 0 to 9. So the highest probability will be with the function with the neuron that the model thinks will be the answer. So for that I have used argmax, and then there is star, which is the target that you can see over here. So for this whatever image was there, the model has predicted 0, and the real value was also 0, and you can see it's tensor of 0, and again here 0. And to see the image, let's say if you want to see the image, you can run this particular line, this transforms.2pil image in bracket ig. You see this is 0 itself. So you can see our program has been working, and we are also getting the results. The losses are decreasing. So if you have any doubts or questions, go to the comment section. If you want a one-to-one discussion, please go on Fiverr and take my gig. It can be a project, it could be anything related to deep learning, data science, NLP, computer vision, blockchain, whatever, all those things. And yeah, so you can also message me on Instagram. I regularly check Instagram. So thank you very much. Bye.